So, Gordon, whenever you're ready,
Okay, thank you very much.
I guess
And
if you're ready, then I can present you. So we have Gordon Semenoff from Vancouver, who is going to tell us about uh, infrared information and accelerated quark paradigm.
okay, thank you very much. And thank you for the kind invitation to speak in this famous seminar. Of course, I would much rather take a trip to Paris than sit here in my home office and give the talk, but being at home does have some conveniences. So what I'm going to talk about today uh, is a very simple question, a rather simple answer, and a sort of fairly interesting paradigm, which is sort of in the some stage of development, so not completely finished, which makes it perhaps interesting. And it's something I've worked on for quite a while. So if you've seen talks by me before, you might have seen a little bits of this, but developed it a little more than it was developed in the past. And so what I want to do is address the problem of infrared divergences in quantum field theory, where interactions are mediated by massless particles. And I will give a lightning review of what they are in abelian gauge theories, where things are fairly well understood. And then I will jump to non-abelian gauge theory, where things are much less understood. But in the context of n equals 4, I'll develop a very simple model where one can say a few small things at least. Okay, so that's what I plan to do here. And as an application of this, n equals 4 super Yang-Mills theory, where I will use it on the Coulomb branch, is like a deconfined gauge theory. And you might wonder if in a deconfined gauge theory, there's such a thing as a color of a quark. Like, do quarks actually have a color quantum number, which is like a global SUN symmetry if SUN is the gauge group, or not? And I found many people have prejudices about this. The fact that such a quark would be created by an operator which isn't gauge invariant in some sense, at least, is a strike against it. But nevertheless, I think the question is interesting. And what I would like to argue is that the answer perhaps depends very much on how you choose to resolve the infrared problem in the theory. Okay, so with that introduction, let me remind what happens in QED. So in QED, anytime you scatter some charged particles, like this, say an electron scattering from an electron by exchanging a photon, what happens in the real physical system is there's a copious emission of soft photons. And the emission is by the ingoing and outgoing lines, something like this. So a whole bunch of soft photons, actually infinite numbers fly off. That's the physical process that actually soaks up all of the amplitude. The amplitude with finite numbers of soft photons coming out is actually 0 because of infrared divergences. The reason why these are important is because if you square this, and then take a sum over the final states of the soft photons, this is actually divergent. There's an infrared divergence in this sum. And of course, that infrared divergence cancels. If it didn't, this theory wouldn't make any sense. And what it cancels against is similar processes, but with internal lines, photon lines, which connect the outgoing and incoming particles to each other. And they also have logarithmic infrared divergences. And when you sum up things like this and square them and add this, in some sense, the cross terms here cancel with appropriate terms over here. That's a result of unitarity. And infrared divergences cancel in the physical things that you want to compute, which are transition probabilities. So this is the textbook story about the infrared problem in electrodynamics. This is actually one solution of the problem. You can see that having to do this, at first sight when I saw this, I thought, well, if you're forced to do this, if somehow nature forces you to compute things this way, your final state is really a mixed state in any scattering experiment, because what you have to do is average over a bunch of final states just per force, a priori. And in fact, that is a correct way to look at it, but there's another way to look at it too, and that is if I transport this diagram with lots of soft photons down here. So there's photons being emitted like crazy. There's a second way to do things, and that's to take this whole object, say the outgoing electron, and all of the soft photons it emits, which are highly correlated with its final trajectory. So this is a well-defined thing to do, and call that a state. In a sense, change a basis in the Hilbert space so that your states are these things. And that's called a dress state. And then there is a particular dressing cloud of photons that in effect is good enough to cancel the infrared divergences. In a way, the way this correlates with the line above is that in the sum over soft stuff, if you put the sum in a coherent state basis, the sum is dominated by one coherent state. And so that's a coherent state one uses down here for the dressing, in a sense. And so the S matrix elements here are directly finite, although in intermediate steps of the calculation, of course, you have to introduce all kinds of regulators because individual Feynman integrals are still infrared divergent, but the dress state can indeed be tuned so that all the infrared divergences go away if you talk about scattering of these things. And those are two different approaches, which for...
Sorry, Gordon, can I ask a question?
Yeah.
So is this way of dressing up the external state unique, or is there some canonical way to do it?
No, there's obviously some non-uniqueness because you could put in, say, a harder photon which doesn't have a divergence, and you don't really know if that photon belongs in your state or not. Right? So it isn't really unique. But the part of it which cancels the infrared divergence is unique. So there's kind of a minimal dressing, and then other things you could do. And to my knowledge, that sort of uniqueness problem isn't resolved. There are other problems here too, besides that one, which you might even think of as being more fundamental. For example, it's a mixture of states with different momenta. So it's never going to be an eigenstate of 4 momentum. You kind of give up on eigenstates of 4 momentum. And in fact, in old constructive field theory, in a way it was, at least indirectly, why the constructive field theorists used to say that quantum electrodynamics is not Lorentz invariant. And that's because these coherent states to Lorentz transform requires unitary transformations that are not proper ones. They don't, in a sense, they don't exist. So there are other problems with dress states too, but it is a way to do things, and it might, in fact, be slightly preferred from the above, because the above is, well, it's a formalism where if you're forced to do it, it creates entropy. Right? So So these two ways of doing things will give identical results for the old-fashioned transition probabilities, the things particle physicists have calculated forever, right? The modulus square of the amplitude. The dress state in its minimal form is such that you will get an identical result for the computation both ways. But then there are certain subtle information theoretic issues which are quite different between the two. So for example, you should really think of an incoming and outgoing density matrix. And then in the first one, you're reducing that density matrix necessarily by tracing over soft photons. In the second way of doing it, a pure state remains a pure state. And those are obviously fundamentally quite different scenarios. So there are potentially physically observable differences between how you do these things. And I would say they're thus far unresolved, and there is certainly some room for good ideas here about where to go. So these things have subtle differences.
Gordon, can I ask a question? Hi.
Sure, hi.
Is the dressed state, can I think of it as being created by a Wilson line attached to the electron operator so as to make it gauge invariant?
In some sense, yes. In some sense, the dressing is there to make the electron creation operator gauge invariant. There are small technical differences between just attaching a Wilson line and putting the dressing, and I really don't have a full understanding of why the small differences and if the real dressing is really a Wilson line. I'd say that's not a completely resolved question either.
Mm-hmm.
I also have a question.
Yeah.
I don't understand the consistency between your first and your second line. In the first line, you argued that it was a loop diagram that connects two legs that allows you to cancel the divergence. But
Yeah.
and then in the second line, you concentrate on one leg, which doesn't seem to know about this loop diagram. So how are these two consistent?
Okay, so I haven't been precise enough in my description of this. That's what isn't consistent. So of course you do this first of all for all the legs. And secondly, this process will contain the internal loops also. Right? So there are loops here.
I see.
And so these incoming and outgoing photons, what happens is the incoming ones, you send in a cloud to interfere destructively with the ones that are produced here. So in some ways you kill all the ones that are produced on incoming legs, then you absorb all the ones that are produced on outgoing legs into your state. And you can do that because the ones that actually are problematic are perfectly correlated with the line that they're emitted from.
Okay, I see. Thank you.
All right. Okay, so that's supposed to be a lightning review of QED. What I would like to do is think about this problem in non-abelian gauge theory. And that's a formidable exercise, actually. There's been tons of work over the years on doing this. There's even a theorem which says the following, that if you come back here to something like this, in a non-abelian gauge theory, you can make everything finite if you sum not only over all final states, like is done here, but also over all incoming states with extra soft stuff. In a way, it's what they would call a resolution of degenerate perturbation theory, in that your incoming state is also degenerate with this electron that came in, or this electron that came in plus a really soft photon, or 2 photons or 3 photons. If you sum over all of that, you're out of the woods as far as infrared divergences are concerned. Well, it's a theorem, so one shouldn't doubt it. But notice if you're summing over everything like that, in a sense, you're giving up on pure states. You're saying that the only sensible thing is some mixed state coming in, which is a mixture of particles and soft quanta, and a mixed state going out. And so what I would like to do is kind of back up from this and ask the question, can one do something better, at least in a simple case? So what I'm going to do is build a model of our favorite non-abelian gauge theory, which is supersymmetric Yang-Mills theory. So I want to build a model in the context of this theory. To do is I'll go to the Coulomb branch. That's somewhere where an expectation value of a scalar field, one of the scalar fields, is non-zero. This say would have SUN plus 1 gauge group. Out here, it's Higgsed by this expectation value to SUN cross U1. So there's a whole short supermultiplet of doubly bosons. That supermultiplet contains spinor and scalar fields. I actually can't remember. Well, it must also contain vector fields. So, it's a half BPS supermultiplet. So there's a 256 of them. Choose a scalar to make things easy. So the doubly bosons are charged under the U1, and they transform in the adjoint to the residual SUN. The spectrum of Yang-Mills in this case, it has, the n equals 4 supermultiplet still there for the SUN, interacting with these doubly bosons, which become massive. And the doubly bosons are at the same time charged under the U1, and all of the SUN n equals 4 fields aren't charged under the U1. Then what I will do is use a U1 electric field as an accelerator for my scalar doubly boson. And a constant electric field, and I will work in the limit where the field is weak or the particle is heavy. And then I will ask the following question. Well, what the electric field does is it gives the W, at least classically, a constant acceleration, constant proper acceleration. So what I will do is I'll consider my space filled with this weak electric field. I want it weak because I want to suppress Schwinger pair production and things like that. There are various reasons to be weak. Also, it's a semi-classical limit here. So I'll take the space filled with the weak electric field. I will inject my doubly boson from infinity, traveling at almost the speed of light, and directly into the electric field. So the electric field decelerates it. So it penetrates the space, it goes in and goes in, but decelerates, finally comes to a stop somewhere inside, turns around and accelerates back out to infinity. And then I will ask the question, what is the amplitude? For this particle to follow its classical trajectory. In the semi-classical limit. So this might seem like a very trivial question, but as I'll try to argue, it's not quite trivial. It actually has some interesting interesting issues associated with it. Okay, so my W boson will follow a trajectory that looks like this sort of Rindler curve with constant acceleration like that. The quantum numbers, well, it has some speed coming in and some position, which is tuned in order to make it follow this trajectory. There's some time of flight across here to my final place. I calculate the classical time, and I ask the question, what is the quantum probability that the particle shows up there at that place where it would have gone if it just followed its classical trajectory? Well, that question I can ask at the quantum level by studying the world line path integral description. So this is one reason why I wanted a scalar particle, because I wanted this description to be simple. And so there, the amplitude, which will have some indices on it, because this is a deconfined quark flying through here. So it has some color index coming in. Right? If it's a quark in some state, it definitely has a color. And of course, color is conserved, so it'll have the same color index going out. And you can think of this line as an index line in a Feynman diagram, if you like. Okay, my notes just decided to go to sleep. It means I'm talking too slowly, which is probably not a good sign. So this amplitude, well, it conserves color at first, and then it has an integral over the, in a sense, the world line proper time, and the embeddings of the world line, e to the I times some action that depends on those things, and which couples to the electric field, and so on. Okay, and this is my quark. Well, I haven't coupled it to the Yang-Mills fields yet. I'm just now thinking of propagation of a quantum particle. But if I couple it to Yang-Mills, there's a fairly simple modification of this formula down here, which I'll do using this eraser transformation that students tell me never to do. Get rid of the delta AB, and of course I should couple it to a Wilson line. Which depends on the trajectory. And if I don't have any n equals 4 excitations around in my initial state, or final state for that matter, this should be taken in the vacuum of the residual n equals 4 Yang-Mills. And of course, it should have these indices on it, something like that. And this Wilson line is, of course, this famous Maldacena one. Which couples to the condensate of scalar fields, something like that, to the one that was condensed. And it can actually be derived that this is the appropriate Wilson line for this kind of W boson excitation. So this W, which depends on the trajectory, one should stick into there. Now the accelerator trajectory, well, with a constant electric field, it's a classical solution without the Wilson line. But actually, it's a highly symmetric classical solution, this Rindler trajectory. It has a lot of symmetry. It preserves some part of the conformal group. And in fact, it's even a supersymmetric trajectory. You can show that it's that the Wilson line for evaluated on that trajectory is half BPS. And that all helps us to conclude the following. Well, actually, just let me do another step before I do this conclusion. So here I'm supposed to calculate an open Wilson line. You might have concerns about gauge invariance, which I'll worry about later. But it also has indices on it. And even so it should be calculated in some gauge fixed n equals 4. But even in the gauge fixed theory, there's a global color symmetry. And really that global color symmetry, I should tell you that this thing has to be global color invariant. And the only way it can be that is, again, if it's proportional to delta AB. So I can rewrite the thing this way. In a sense, as a trace over the operator. So this is over the matrix indices. And so this is just a trick using global color symmetry. And maybe I don't even need it here, but it is handy to do nevertheless, because it will help in some computations. Okay, so now with the constant electric field, the accelerator trajectory is a solution. One can actually show that that solution also is a zero of the functional derivative of the expectation value of this Wilson line by the embedding function of the path. Okay, so you take a functional derivative by the path, and then you set the path to that classical one, and that functional derivative is still 0. That means that in this world line integral, the classical path actually is still the same as it was without the Wilson line. So the semi-classical amplitude here something like this, e to the I. The action evaluated on the path on the classical solution times this open Wilson line traced also evaluated on the classical solution. So this will take as the semi-classical limit of this problem. I've ignored a whole bunch of things like matter loops. Those are suppressed for various reasons. In large N, they're suppressed because they're fundamental, because the W boson is a fundamental representation object. But even without large N and at large mass, they're also suppressed. And so in the large mass limit, and the only thing to compare the mass to is the electric field, this should be an accurate estimate of the amplitude I'm looking for. And of course, without this correction, this amplitude is just a phase of some kind. And so the probability is that thing squared is 1. And that just says that in the semi-classical limit, the probability that the particle will follow its classical path is 100%. And then that can perhaps be modified by whatever this thing is. Okay, so now I have a Wilson line, which I need to compute, the second thing. So it's integrated along something like this. Again, there are gauge invariance issues because the endpoints are at some finite place. So I will not trust this unless I could push the endpoints right to infinity. Even then, there might be trust issues. Even then, I might only be interested in some asymptotics where the endpoints go to infinity of this amplitude. But in any case, it's sort of interesting to ask the question, okay, how does the Wilson line correct this? And of course, it should, in the leading order, give something that looks like this. Let's see. I always have trouble drawing these fat graphs. Okay, slightly messy, but there's a first correction where this is an exchange of an A or phi particle. The other thing is the AA correlator in the Feynman gauge looks something like this, where this is X and this is at Y, this is mu, this is nu, and then the indices, if this is A, B, C, D, delta A, D, delta B, C for UN symmetry. The scalar propagator, similar indices and everything, is the same as the above with eta mu nu replaced by delta ij. So they're very similar. What's more, when you take the combination of scalar and vector propagator that you need to make this thing and evaluate them with the endpoints on this accelerated trajectory, so it's something like x dot prime AA plus x dot prime phi. This turns out to just be a constant. And I have to look at my notes to remember exactly what the constant is, but it's some simple thing. It's got the acceleration squared over 16 pi squared. And then it just has the Lie algebra, the gauge group indices like that. So that's very convenient. Once I know that, you can immediately write down the answer for this correction. And in fact, you could dream of improving it a lot. And that's because any propagator that goes from the Wilson line back to the Wilson line will always occur in this combination, will always be a constant. So you could dream of calculating higher orders. Well, let me just calculate the leading order for now. Well, let me talk about that too. So the leading order here. Well, this conserves global color. So you had color A coming in here. They follow the color line, it's conserved. Here also, if you follow the line, it's conserved. And then there's color circulating around this index loop. So that'll just give a factor of n, which is in fact needed in the large N expansion. So my amplitude here. There's the on-shell action, which we don't care about very much because it just gives a phase to this amplitude. And then it turns out that this thing, well, if the propagator is a constant and it's real, there's an I that comes down twice. So there's I squared, which is -1. So this thing is actually real and looks like this. The Swift coupling up here. 32 pi squared down here. And then A. And then the total proper time of this trajectory, which is the Riddler time. I haven't defined it yet. It would take some formulas to write, so I won't, but let me just write the proper time during which the quark propagates from here to here. Okay, that's kind of simple. And corrections to it are also simple, except when you have internal vertices. Okay. This result should strike one as being strange, in fact, maybe even pathological. And that's because I would expect that, well, maybe it won't exponentiate exactly because this is non-abelian gauge theory, that this is an expansion of some exponential. And then we see that it seems that that exponential would be damping like a Gaussian in the proper time. And that tells me if you wait a very short time, like the inverse of the acceleration here, that this amplitude just goes to zero. It drops off to zero faster than what one would expect. In fact, really, if you're only interested in the asymptotics of large proper time, you could only honestly say that this amplitude is zero. So what happened? Well, I looked at this process. What I've forgotten about is gluonic Bremsstrahlung. Right? My discussion from before should have educated me enough that I should have at this point also looked at the amplitude for emitting a soft vector or scalar particle on shell, which flies off to infinity undetected, and that should have been taken into account somehow. And indeed, that seems to be the correct reasoning. A reason why I never thought about this, actually, in self-defense, is that this doesn't have an index loop. So it has a G Yang-Mills at the vertex here, but no factors of n to compensate it. It'll nevertheless be important to us, even in the large n limit, which now becomes rather subtle. You can also see that the color degrees of freedom kind of propagate in a strange way through this. The original quark color is carried away by the particle that flies away undetected, and every kind of particle flies away with equal probability undetected. And so this B should just be summed over all the colors. So this process of emitting a Bremsstrahlung will randomize this final color state somehow. And since the index structure over here is different from over here, even if this diagram cancels the infrared divergence, it's only going to do so for some combination of color indices. Right? It's not going to be a global panacea. On the other hand, it's all we have. So let's proceed. But let me give you a little more, perhaps a few interesting comments about why the problem here is forgetting about the Bremsstrahlung. Just some comments. So in some old work for this very problem, one can actually sum up all of the so-called ladder diagrams. So all the diagrams that look like that, where every particle begins and ends. So there the propagator is a constant. So all you have to do here is solve the combinatorics of, you know, the group theory at the vertices. And that can be done using a matrix model. And so the sum of all these things is known. And it looks like this. And it indeed has this exponential G Wang Mills squared without the n. It's not the Tuft coupling up here. 32 pi squared A tau p squared. And then Laguerre function, some kind, 1 over n in front of it, of order n1. And basically the same thing as the exponent, maybe with a factor of 2. And as promised, there's a kind of at least a quasi-exponentiation here, and this thing really does damp like a Gaussian, this sum of diagrams. Now, the sum of diagrams is a selective sum, so you don't really know the accuracy. Actually, in Euclidean space for the circle-Wilson loop, there one could show that corrections, some of the leading perturbative corrections from the stuff that's left out of this sum, actually canceled, and then there's a very nice proof by localization in that case that a result, the analogous result is exact. This proof by Vasily Pestin that the n equals 4 functional integral and that the half BPS sector actually localizes. So there's a proof there, but here on the Lorentzian side, I don't have this beautiful proof. In fact, mathematically, it looks difficult with Lorentzian signature. So I don't know that there aren't corrections to this. That would be an interesting thing to look at, actually, but to my knowledge, hasn't been done. But in any case, it does sum up to something which looks like that. Surprisingly, if I take the planar limit, one could do that. The result comes mainly from the Laguerre polynomial. In the large n limit, it goes to infinite order. And this looks something like you get the square root of what was upstairs with an extra n and a factor of 2. Somehow the planar limit decimates the Feynman diagrams in such a way that the sum is not so severe. The sum turns into something that's oscillating. And has this sort of phase factor. It's no longer damping like a Gaussian is the point. And so taking the planar limit has kind of gotten rid of this damping problem. And that I take as further evidence that in the amplitude, Bremsstrahlung is suppressed. So somehow this is a place where you actually recover unitarity by doing large n. It's interesting. And that I sort of take as just consistency of this picture, that the problem, what's leading to this damping, is the loss of unitarity because I've forgotten about soft Bremsstrahlung. The other thing is, well, this is large n and n equals 4 super Yang-Mills theory calculation of some kind of Wilson loop. You could compare it with strong coupling. And ask if it's the area of some kind of a surface whose boundary at the boundary of ADS space is the Wilson loop. And indeed it is. Indeed, the surface is an ADS2 section of ADS5 with the time oriented in a funny way that it looks like it has an event horizon on it. It's a sort of a wormhole. And this quantity up here is the area that's between the wormhole and the boundary of ADS on that surface. So this does actually have a check in large n, in a sense, it's strong coupling. Okay, but this non-perturbative story is not the direction I want to go in here, but I just mentioned it because it's sort of some interesting pieces of the puzzle. I will find indeed that Bremsstrahlung, even if it looks suppressed, is important. And that's a lesson one might drag over to the ADS side of this story to understand what's going on there. Is the classical limit of the string theory, the supergravity limit failing somehow. And that I will leave, in a sense, as an open question. Of course, the large n limit there isn't a problem with, so it would have to be corrections to large n. And that I would say is a completely open discussion. Okay, so what if I now correct my perturbative calculation? For the for emitting the Bremsstrahlung. So what I'll do is I'll put this in a density matrix. So somehow in the middle of my Feynman diagram are the two legs of the incoming density matrix. Then I have the Wilson loop up here on one leg, Wilson loop down here in the other leg, and here's the outgoing stuff. All right, so if I put in a density matrix AB, one of these indices is B, one of them is A, and it propagates through here, and multiplying by the amplitude and the amplitude dagger on each side of rho in AB gives me the outgoing density matrix. Then what I've already computed is that correction. So there's a plus between these. And then there's that correction. So these are things I've already computed, and these are going to damp my density matrix, right? They decrease it. So that's another more evidence that unitarity is the problem here. And then I want to include soft Bremsstrahlung and a trace over soft Bremsstrahlung to make a final reduced density matrix. So how do I do that? Well, I need this line to emit something, and then the trace says I'll match it up with something that emits something down here. And really what I do is just, identify these, integrate over the momenta, sum over their indices, something like that. And I drew this in fat graph notation, and these I didn't. If I had, they would actually look kind of similar. It's just that this one goes from one line to itself, this one too, and then this one over here from, well, one line to the other. But you can see already that, first of all, this is the on-shell part of the propagator. It turns out that the thing that contributed here was also the on-shell part of the propagator. So in fact, numerically, they're identical. There's a 1/2 factorial here and here because you're expanding an exponential. So these add together. There's also I squared and minus I squared, whereas this one there's I times minus I, so they have opposite signs. So this is ripe for cancellation. The only fly in the ointment is that the indices here are strange. Here an incoming index A remains A through this fat graph, but here it doesn't. Here an incoming index A kind of is transferred over to the other side. And the outgoing indices have to be matched and subbed over. So if I put that all together, I can actually put it into a fairly suggestive form. Okay, so after some proper time, this outgoing reduced density matrix the incoming density matrix, whatever it was, minus a trivial one, trace of rho in, over n. This is a piece that I would say is damping like a Gaussian. And then a correction term. It looks like this. And then higher order corrections. So this is my reduced density matrix, and now it has a rather interesting form. First of all, if I take a trace, I find that the trace of the reduced density matrix is just equal to the trace of the incoming density matrix. So indeed, I've recovered unitarity in a sense. Beyond that, if you look at the first term here, this is the difference between whatever my incoming density matrix is and one which is just a maximally mixed state of all the colors of the incoming quarks, right? This is a mixed state density matrix. In fact, it's as mixed as it can get. Its eigenvalues are all 1 over n, this is diagonal, and this is the difference. And this formula tells me it's that difference that damps out with time. So this is the thing that seems to be going to 0 quadratically with time. And then the thing that survives is just this. So what it says is whatever my quark was coming in, if I dare to fix its color and think about it having fixed color, in a short time, that color, the quark will go into a mixed state. And it goes into a mixed state because of this information loss, gluons flying away to infinity undetected. And that mixed state will just be a mixed state with every possible color appropriately normalized. So in a sense, color washes out, or the quark loses its memory. I'd call this memory loss. Okay, so that's interesting, and that seems to be a result here. So this way of doing things, of in a sense, looking at inclusive processes, necessarily loses information in the sense of this memory loss paradigm. Okay, I just want to look at the time here. I see I'm pushing the time. Okay. What's more, one can give a somewhat convincing argument that this term, this thing I call quadratic damping, that if you really take tau p large, it sort of stops making sense because it's no longer perturbation theory. But I could look at it that way if I calculate it a little bit differently from the way that I've done, by going back to the actual Feynman integral and putting in an infrared cutoff. If I can do that, then I find its large tau p behavior is linear when it has an infrared cutoff. Right? The a tau p squared, this sort of proper time squared, goes to a proper time linear times the log of, say, the acceleration divided by a fundamental cutoff. Right, so one can demonstrate more or less directly that this has something to do with an infrared divergence. Okay, the other thing I could do is introduce a detector resolution. In the argument above, I traced out all gluons and scalar particles, all the stuff that flies away, assuming it's all goes away undetected. But that's not how the real world works. If you had a really hard gluon, I think you might detect it. So in that case, I should probably only trace out the stuff that I wouldn't be able to detect. And that's the stuff that's below some detector resolution. I could fake a detector resolution in the following way. It's kind of easy here. I could say that my detector switches on and detects particles only in some interval of time here. In fact, let me give it an interval of proper time. So there's some shorter interval of time when I can detect particles, and then the rest of the time not. Then this formula no longer is perfect. Some of these corrections will only have this sigma p instead of tau p in them. So one can go back and look at this. It's kind of easy. And the result is, will look something like this. Okay, with a detector resolution. What do you get? Actually, the first term is just identical. So the memory loss doesn't change. What changes is the second term, which remains this colorless thing. Right, so the memory loss says that any evidence of the initial color goes away really fast. And the second thing also goes away, but at a slower rate. Like this. And this slower rate one can understand perfectly, and that's because I've only taken into account some particle production, not all. But I'm still looking at that part of the density matrix where the outgoing state has a quark and nothing else. And so I don't expect unitarity here, because there is some probability for producing a hard gluon and hard scalar particle that has been left out. In fact, this damping rate, in a sense, you can think of this coefficient as a damping rate, which tells you how fast the probability goes from just a quark coming out and far infrared particles to a quark plus some hard massless particles. It looks something like this. So something one can actually extract from this calculation. Which basically tells you how fast things are turning over here. And this is interesting. In fact, this thing for Rindler trajectory, the proper time goes like, when it's large, goes like the log of the observer time. So this is something like a log of the time in the rest frame watching this normalized by a. Right, so somehow it goes away again logarithmically, like you'd think of an infrared divergence. And if you do the calculation with infrared cutoffs, indeed this is replaced by a log of a cutoff, which is basically the detector resolution. So something finite now. Whereas if you do the calculation with cutoffs, this first thing still has a fundamental cutoff in, like a gluon mass that you really want to set to 0 at the end of the day. So again, you get this washing out of color very quickly. And then there's kind of a slower decay, which means that you're mixing with states which have massive particles produced. Okay, well, I'm running out of time. So let me just say what happens if you include if you look at dress states. So a dress state is something like the incoming quark, and then plus say between a fundamental and a cutoff and a detector resolution. Some photon or gluon, I guess, with x mu dot of tau, say the final. So this would be the dress state you attach to the final thing, plus AI, okay, the scalar particle. So something like this, something traveling with constant velocity that has this sort of Fadeev-Coolidge-like form. With the final constant velocity at the end of the trajectory. And of course, these being creation operators for fundamental representation, particles have indices and B is summed over here. So it looks something like that. And somebody asked me if this comes from a Wilson line. It's not exactly. A Wilson line has extra things in here, which I don't really understand where they go. Maybe I just don't understand and someone else does. This I'm not sure of, because there is some literature about this, but this doesn't exactly come from a Wilson line. So I'd call this the dressed quark. Notice it has a well-defined quantum number because this is the A state of a fundamental representation. And then here the vector and scalar particles are in the adjoint, but they combine with the fundamental, and then summing over B this way projects out the same fundamental representation. And in fact, it has the same index, right? So the free index here is this first index A. If you calculate the amplitude of these guys and this ratio of cutoffs, it turns out that all of these issues with indices go away. And in fact, you get a damping rate, just like we did before, which matches. It depends on the detector resolution, the upper cutoff here. The lower cutoff is a fundamental cutoff. It's canceled. So this is how dress states cancel things. And the color charge is just preserved. So this shows that there's an absolute fundamental difference between two ways of doing things. The first way, in the undressed state, the color charge goes away in a hurry, becomes completely randomized, and then this process takes over. For a dress state, it's exactly the same process. The damping factor is actually identical. For the dress state, all there is that process, and the color is conserved. Okay, so that looks quite different. Now, I would say it's maybe not as different as it seems, because this dress state is highly delocalized. Right? It has the quark coming in, and then as it comes in, it's spitting out these massless particles, which fly away from it at the speed of light. It's a heavy quark, so it's not ever going to go the speed of light. So these massless particles separate and go far away. And in some sense, the color charge in the state is very non-locally distributed. Some is flying away at the speed of light, and some is still there, and somehow they combine together to make the color of the quark. But if you ever did a color measurement, if there is such a thing, tried to measure the color, presumably you could only do that locally. And in a way, you'd be back to the other story in that in this dress state, the fact that you can't see the charge of the vector and scalar particle, the color charge, would make it completely random, and that would randomize your answer anyway. So it could be for practical purposes. These two aren't very different, but at least in principle, in keeping track of quantum numbers, it seems like the dress states in some ways do a better job. There it seems like the color of a state actually is conserved. Okay, and I see I've run out of time. Do I have time to just make a comment?
Sure, yeah, go ahead.
Okay. There's another interesting angle about this, which I haven't published because I don't understand everything. But if you consider back-to-back Rindler trajectories like this. Okay, so these are always outside of each other's event horizon. So I set this up so that classically, these are never in causal contact. So in the semi-classical limit, you would expect that one guy propagates over here, the other guy, well, it should be an anti-quark for this to be half BPS. It's funny because quark and anti-quark aren't half BPS if they're sitting still, but if they're accelerating, quark aren't half BPS, it's quark anti-quark. But anyway, they're never in causal contact, so they can't talk to each other. And in the semi-classical limit, I guess the world line path integrals just factorize. And in fact, you could dress that up to look at the S matrix for producing stuff. And the S matrix as a matrix factorizes. But if you start calculating an amplitude, there are for each one of them the corrections I've already talked about. But there's an additional one now, because of course they can exchange an off-shell gluon. And if I write that as a fat graph, which I probably should have done if I was going to be neat about it, that exchange of an off-shell gluon, which here is a constant, by the way, these propagators are constants just like the other ones. Well, it correlates the final states and the initial states in a funny way. And this seems to be a real process. An example of what's called entanglement harvesting. A really simple example where you can solve everything and figure out what entanglement is generated by this. And then you might ask, isn't this acausal somehow? And I think in the spirit of this subject, it really isn't. So what's happening here is the S matrix, if you look at it as an operator, the thing that propagates the initial states to the final states, thing you would call S matrix, as an operator, it actually factorizes into something for the left half and something for the right half. And you can see that the commutators and the formulas that used to factorize it, they have actually commutation relations in them when the commutators fields vanish outside of the light cone. So that's all nice. S matrix factorizes. So what about this? Why isn't this factorized? Well, this isn't factorized because you've assumed something about the incoming state. You've assumed that besides the quark, all you have here is the ground state. And so this is kind of the obvious fact that even if a matrix is factored into a product of two matrices, if you take a matrix element of that product, it doesn't have to be factorized and generically isn't going to be. And so the correlations here are actually in the fact that you have ground state on both sides. And that's already in some sense a highly entangled state of local variables, right? It's highly correlated because you know if there's nothing here, there's also nothing over there. There's a kind of obvious correlation. And in fact, in terms of local variables, the ground state of a field theory has divergent entanglement entropy in it. And this sort of process is just a way of flipping a little bit of that entanglement entropy from the ground state to these quarks. And you could just calculate how entangled they are. And this also has an infrared divergence in it. But this infrared problem is fixed very much like in the way that I described for a single quark by looking at evolution of Bremsstrahlung and so on, emission of Bremsstrahlung, so competing things like this, and tracing them out, and they seem to go everywhere. So this is canceled by some cross terms in such a trace. Anyway, this is one very interesting thing that one can do with this model, which I haven't published yet because I'm still trying to understand all of the details. All right, and with that, I'm not going to take, I've already gone over time. I think my conclusion should be fairly obvious, so I'll thank you. Thank you very much.
Thank you very much, Gordon, for the very nice talk. So the floor is open for questions.
Maybe I can ask one, Gordon. Is the fact that you are doing all these calculations in what is an unstable background, could it be actually producing, some unphysical conclusions? Even though you said that's a non-perturbative instability indeed, but somehow you are still in some unstable geometry. And
this is something I've thought about, and I managed to convince myself that in this weak field limit, it isn't unstable enough because competing processes are exponentially suppressed, like Schwinger process or Drell-Yan or things like that, things that compete with this. For example, if it were a quark and antiquark annihilating and producing a hard gluon and creating a pair again. So there are competing processes, but I managed to convince myself that in this very heavy quark limit, they should indeed be suppressed. Now, I don't really know that in a non-perturbative sense. So there is a hole in the argument that maybe something non-perturbative actually happens there, but perturbatively, there is very tiny exponentially suppressed corrections.
mm-hmm. Well, thanks.
Sure.
Well, so since I hear no other question, can I ask one more? Is this, you said this is a BPS story. Is this basically the analytic continuation of these circular loops on a sphere that Kostya and maybe you or others were studying, or that's a different thing? I mean, why is this a BPS?
Because you can find a killing spinner, but it is basically the same, that this is an analytic continuation of the circle. Well, in this case, this thing that I've drawn here that's on the screen, if you tune the distance of closest approach properly, so somehow the curvature and positions, and it's a quark anti-quark, you could show that the Wilson line operator commutes with half of the supercharges.
I see.
And it is the same argument as the Euclidean circle. So in some ways, this is the opening up of the Euclidean circle.
Oh, I
but
see.
You can see that the physics somehow, the conclusions are quite different from that of the circle, which was rather mild and didn't have divergences of any kind and so on.
That's interesting.
Gordon?
Questions? Yes, go ahead.
Yes.
Is it possible to speak about scattering of two quarks in this context?
I don't see why not, but if you go away from the scenario I've had here, that I've discussed here, you probably are going back to just having to draw conventional Feynman diagrams because in a way you lose the half BPS nature. Actually, two quarks just sitting side by side, in this case, is half BPS.
Yes.
Right. So if they scatter, it might violate it only weakly. And so maybe there is something to be understood there. But I don't know. I haven't really looked at that. It's an interesting suggestion, perhaps.
Thanks. Another small question. If you consider the asymptotics of this of one accelerated quark, and then so you have some boundary, some initial and final states where you switch out the W field, so the quarks are free. So can you you can make a dilaton, you can shrink the region where the quark is accelerated. So is it possible in this case to speak about cusp anomalous dimension? I mean,
yeah, actually, I didn't mention that. But you could take a limit here where the acceleration is very high for a short time. It's possible to take that limit. And then this factor in front here is just the cusp anomaly, right? In a way, this is the double log that appears in the cusp anomalous dimension for, you know, when the lines coming into the cusp are null. Right, there's a log from them being null and then a log from the cusp angle itself. And these are just those two factors. And this is precisely the cusp anomalous dimension. And you sort of get that by just shrinking, you know, scaling A and tau P in such a way that I think, well, maybe this has to diverge. I don't remember what the scaling is, but one could just sharpen this up to be basically that, right? And that might be interesting too, because the corrections to it are known at higher orders.
Yes, thank you. I mean, I remember in 2 dimensions there are these long strings which resemble to your accelerated quarks, and they have a quite non-trivial scattering. The long strings that Juan considered in connection with the Euclidean black hole, no, Lorentzian black hole in 2 dimensions.
Yeah, this I don't know. I don't know much about. So
No, maybe it's not related. It just I just said it because it's possible that these 2 quarks have a very non-trivial scattering.
Yes, that certainly could be. And there should be an infrared problem to solve there. So that could be quite interesting, yes.
Okay, thanks.
Okay, so if there are no more questions, I propose at least that we should stop the stream, and then if there's still people interested in discussing with Gordon, they can stay on. So let's thank Gordon again. So thank you very much for giving this very nice talk.
Okay, thanks.